Now let's rationalize the trigonometric identities. Prove the identity and state the domain of theta in each case. Now, this is a little bit trickier than what we did before. We just used to plug in identities and things would just follow along as like butter. They would just eventually end up proving the equation. But this is just a little bit different. Let's take the left hand side. Now 1 minus sine theta over cos theta. Once you actually try to do this, just plugging in identities and stuff, you'll find out that it's really not that easy. Now there's a very simple way to do things like this. Basically you have something in the denominator which is cos theta. So what you can do now here is basically, you see the numerator 1 minus sine theta. Well, now you can just basically multiply it 1 plus sine theta over 1 plus sine theta. Then this entire thing equals to 1, so it does not affect the value of the equation. But once you actually do the multiplication, this is basically what you call rationalization. This is the conjugate of the numerator. 1 plus sine theta is the conjugate of 1 minus sine theta, and you take the conjugate on both the numerator and the denominator and multiply it with the original expression. What that does is basically this 1 minus sine theta into 1 plus sine theta becomes 1 minus sine square theta, using the algebraic identity that a square minus b square is equal to a plus b into a minus b. And so that's how you get this. And in the denominator, cos theta is just being multiplied with 1 plus sine theta. And 1 minus sine square theta is equal to, using the identity, it is equal to cos square theta. The identity that cos square theta plus sine square theta is equal to 1. So cos square theta is equal to 1 minus sine square theta. So you have this now. And what you can basically do is, this cos square theta will be cancelled. The one of the cos square thetas, the cos square theta over cos theta is equal to cos theta. So basically you can cancel out this cos theta and the 2 from this. And so you get cos theta over 1 plus sine theta, which is the right hand side. And the domain, well, the domain is basically all real numbers, but theta cannot be equal to 2n plus 1 or into pi by 2. Why can it not be equal to 2n plus 1 over pi by 2? Well, because the denominator can never be 0. Because once the denominator becomes 0, the function becomes undefined. Anything divided by 0 is undefined. And basically 1 plus sine theta cannot be equal to minus 1, because 1 minus 1 is basically just 0. So how is 1 plus I'm sorry, this has been a mix up over here. Basically 1 plus sine theta can never be equal to 0, because the denominator cannot be equal to 0. So sine theta cannot be equal to minus 1. When is sine theta equal to minus 1? Well, when the value of theta is 2n plus 1 into pi by 2. This n can be any integer, any natural number, basically 1, 2, 3, 4, 5, 6, 7, 8. And once you plug in, say 1 instead of n, so that just becomes 3 pi by 2. The value of sine theta at 3 pi by 2 is minus 1. Similarly, when the value of n is 2, it becomes 5 pi by 2. And again, the value of sine theta is minus 1 at 5 pi by 2. So yeah.